Let's talk about everybody's favorite part of trigonometry, sine, cosine, and tangent. And so each one of those three kind of have a proportion that has a rule about it when it comes to right triangles. And the proportions are really easy to remember by using this phrase, SOH. TOA. And if you want to know what each word stands for, you can just look over here at your graph. And so let's take a moment to sort of explain how it's possible that a triangle can always be so proportional, how these rules are always the same proportions. And so we have this right triangle. Well, all three angles have to add up to 180. Well, this one's already 90 degrees. That means the other two sides, let me go ahead and mark this one, this angle, not sides, angles. Keep saying that. These two angles have to add up to 90 themselves. To 90 degrees as well. The reason why they have to add up to 90 degrees is because they have to add up with this number to get 180 in total. And so whatever this angle is, if you know this one, then you have to know the other one. So for example, if this angle right here is 1, then the other one has to be 89 degrees. If the second one is 3, then this one has to be 87 degrees. If this angle over here is 10, then the other one has to be 80 degrees. And this keeps on going forever and ever. If we have one that's messed up my colors there, 80 degrees. All right, and if we have one that's 30, the other one has to be 60, and like I was saying, this goes on and on and on. If you know one, then the other one has to be the other number that's needed to add up to 90. So if one's 45, the other's 45, and so on and so forth. If this one is 50, then this one has to be 40. And these are all proportional. So they're kind of like ratios almost. You can think of them that way. And since the angles are ratios to each other, well, then their opposite sides are ratios to each other. And what you can do, based on the angle, you can make a ratio or a proportion using this phrase or using these equations. So let's go ahead and try an example and get some trigonometric ratios going. So let's say we got a triangle here, and let's say that the three sides are, well, let's go pick that back to blue and pick our pencil. Let's say the three sides are 3, 4, and 5. 3, 4, and 5. And let's call the angles X, Y, and Z, because it doesn't really matter. For now, let's just say the angles are X, Y, and Z. Well, let's go ahead and find the sine, cosine, and tangent of angle X then. So X is just some random number. It could be 39. It is a very specific number because of the sides, but it's just some random number. Let's go ahead and leave it as X for now. Sine of X would equal the opposite over hypotenuse. Well, the opposite of angle X right here, well, that's just 4. 4, and the hypotenuse is the longest side, or the side that's opposite to the right angle. Well, that's 5. 4 over 5. What about cosine? Cosine of X. Well, cosine of X would be, well, that's adjacent over hypotenuse, and adjacent is the side right next to it. And you might say, well, there's two sides next to it. And I would say, well, yeah, there are two sides right next to X, but one of them is the hypotenuse, so the adjacent is the other one, which is just 3 over the hypotenuse, which is 5. And then, of course, tangent is the exact same thing, just opposite over adjacent. Well, the opposite to X is 4, and the adjacent is 3, so it's just 4 over 3. And the next thing you might point out is, Mr. Anderson, if I double all these sizes, the angles won't change. If I change this to 6, and this to 10, and this to 8, well, then I just made the whole thing proportionally bigger. The angles are all the exact same. But you said the sine of X is always 4 over 5, that this always works. It's always basically 0.8 in this case, 0.8. And we're not going to use that, so don't write that down. I'm just kind of giving you a decimal number to look at. But if I double the sizes, the angles are the same. Is it still proportional? And the answer is yes, because the opposite of angle X is now 8, and the hypotenuse of angle X is now 10. 8 over 10 simplifies to 4 over 5, so it's still the same. The same thing is true here. It's 6 over 10 simplifies to 3 over 5, and 4 over 3 simplifies to 8 over 6. I'm sorry. it's 8 over 6 simplifies to 4 over 3. The new tangent is 8 over 6. Excuse me. So yes, these formulas always work. So let's go ahead and try one more example here. Let's say we have a random triangle, and let's say this time we have 5, 12, and 13. And this time let's call the angles, let's call them EDF. So DEF. And I'm just being OCD at this point. DEF, because it doesn't really matter what we call them. We just call them something. Well, what's the sine of angle E? Well, the sine of angle E would just be the opposite over hypotenuse still, or SOH. Well, opposite of angle E is 5, and the hypotenuse is 13. So it's just 5 over 13. And the cosine of angle E would just be the adjacent over the hypotenuse, which is just 12 over 13. And the tangent of angle E would be opposite over adjacent, so that's 5 over 12. So now I ask you, what happens if I go with the other angle? What happens if I go with the other angle over here, this F? Well, let's find the sine of F. It's pretty simple. We just take the opposite, which is 12 over the hypotenuse. So that's just 12 over 13. We take the cosine of angle F. Cosine of angle F would be the adjacent over hypotenuse, which is just 5 over 13. And the tangent of angle F, well, that's just opposite over adjacent, which is opposite is 12, adjacent is 5, so just 12 over 5. And you might have noticed some things. You might have noticed that the cosine of F is equal to the sine of E. They're both 5 over 13. They have the exact same proportion. And you might have noticed that the cosine of E is then equal to the sine of angle F. Well, that's because the two angles are kind of opposites to each other. They both add up to 90, but they're the opposite numbers. They're the opposing numbers. And sine and cosine are kind of opposing to each other. So these are both equal. And then you might also notice that the tangents, pick a better color here, the tangents are inverses to each other, the two angles. And you might say, well, Mr. Anderson, what about this last angle here? What about angle D? And the answer is, well, angle D, well, that is a 90-degree angle. And its opposite is its hypotenuse. So if I, for example, wanted to take the sine of angle D, I would get basically hypotenuse over hypotenuse, which doesn't make any sense. It doesn't give me a proportion. It just gives me 1. So we can't take the sine, cosine, or tangent of the right angle. So we don't concern ourselves with that.